This video is for beginners who are new to exploring AI locally. If you know every basic thing like quantization, GGUF, Ollama, vLLM, multi-GPU inference, then you can skip this video. So let's start exploring the local LLM. Not long ago, running a large language model required access to expensive cloud infrastructure equipped with dozens or even hundreds of enterprise-grade GPUs. Today, thanks to advances in model architecture, inference software, quantization techniques, and consumer hardware, many powerful open-source AI models can run efficiently on your personal computers, gaming desktops, workstations, and even some modern laptops and smartphones. Running AI locally means the model executes entirely on your own hardware rather than on a remote cloud server. Once the model is downloaded, prompts, documents, and conversations remain on your computer, offering greater privacy, offline availability, lower long-term costs, and complete control over the AI environment. For developers, researchers, businesses, and privacy-conscious users, local AI has become an increasingly practical alternative to cloud-hosted services. Whenever you interact with cloud-based AI services, such as Claude or Gemini, your prompt travels over the internet to a data center. There, powerful servers containing multiple GPUs perform the required computations, generate the response, and send it back to your device. This process is known as cloud inference. Local AI follows a fundamentally different approach. Instead of relying on remote servers, the entire AI model resides on your own computer. Every calculation required to generate text is performed locally by your CPU, GPU, or a combination of both. Once installed, no internet connection is required for inference, unless the application itself requires online resources. This architecture offers several advantages: complete privacy, since prompts and documents never leave your device; offline functionality after the model has been downloaded; no recurring subscription fees for inference; greater flexibility for customization, experimentation, and fine-tuning; reduced latency if you have a powerful PC and the model fits on your machine, because responses are generated directly on local hardware. The core of every model consists of parameters, commonly referred to as weights. These weights are numerical values learned during training that determine how the model predicts the next token in a sequence. For example, a 3 billion parameter model contains approximately 3 billion learned numerical values. A 7 billion parameter model contains approximately 7 billion parameters. Modern frontier models may contain hundreds of billions of parameters, or even use mixtures of experts commonly referred as MOE, containing trillions of total parameters. Generally speaking, larger models possess greater reasoning capability, broader world knowledge, and stronger language understanding. However, they also require significantly more computational resources and memory during inference. Each parameter occupies storage space. The amount of memory required depends on the numerical precision used to represent these values. For instance, a model with 8 billion parameters stored in 16-bit floating point requires approximately 8 billion times 2 bytes, that is 16 gigabytes. This estimate only covers the model weights themselves. Additional memory is needed for activations, temporary tensors, the tokenizer, the operating system, and the key value cache used during inference. Consequently, actual memory requirements are usually several gigabytes higher than the raw model size. Training and inference are often confused, but they represent entirely different stages of an AI model's lifecycle. Training is the computationally intensive process through which a model learns by adjusting billions of parameters using massive datasets. Training may take weeks or months on thousands of GPUs and consumes enormous computational resources. Inference, on the other hand, is the process of using a trained model to generate predictions. During inference, the model's parameters remain fixed. The model simply performs mathematical operations to predict one token at a time, based on the input prompt and previous context. Running AI locally refers exclusively to local inference, not local training. Language models do not process entire words directly. Instead, they operate on tokens. A token may represent a complete word, part of a longer word, a punctuation mark, a number, a white space character, a special control symbol. For example, the word unbelievable may be divided into multiple tokens depending on the tokenizer used by the model. The model predicts one token after another until it reaches a stopping condition or generates the requested output. Performance is commonly measured in tokens per second, which indicates how quickly a model generates responses. Although CPUs can perform AI inference, GPUs are dramatically better suited for this workload. Modern language models rely heavily on large-scale matrix multiplication. GPUs contain thousands of processing cores capable of performing these operations simultaneously, whereas CPUs typically contain only a few dozen high-performance cores optimized for sequential tasks. Because of this massive parallelism, GPUs deliver substantially higher throughput for AI inference. VRAM is the dedicated memory located on a graphics card. During inference, model weights are ideally loaded entirely into VRAM. Since GPU memory is directly accessible by the GPU, inference becomes significantly faster. When the model exceeds available VRAM, portions of the model must be transferred between GPU memory and system RAM over the PCI Express bus. This introduces substantial latency and reduces generation speed. For local AI, VRAM capacity is often a more important factor than raw GPU processing power. One of the most important innovations enabling local AI is quantization. Quantization reduces the numerical precision used to store model weights while attempting to preserve as much model quality as possible. Instead of representing each parameter using 16 or 32 bits, quantized models may use 8-bit integers or 6, 5, 4, 3, or 2-bit representations. Lower precision dramatically reduces memory consumption, allowing larger models to fit into consumer GPUs. The primary trade-off is a potential reduction in model accuracy, although modern quantization techniques often preserve surprisingly high performance. 8-bit quantization offers minimal quality loss while nearly halving memory usage compared to FP16 models. Advantages include high reasoning accuracy, strong instruction following, better numerical precision, suitable for professional workloads. The downside is that 8-bit models still require relatively large amounts of VRAM. 4-bit quantization has become the industry's preferred compromise between model quality and memory efficiency. A 4-bit model often occupies approximately 1/4 of the storage required by a full precision version, while maintaining performance remarkably close to the original. Most community-distributed models intended for consumer hardware are released in 4-bit variants because they provide an excellent balance between speed, memory usage, and inference quality. 2-bit quantization pushes compression to the extreme. Such models require significantly less memory and may enable much larger models to run on modest hardware. However, reducing precision this aggressively introduces greater approximation errors. While some tasks continue to perform well, complex reasoning, coding, and mathematical accuracy may decline. Active research continues to improve ultra-low-bit quantization, making 2-bit models increasingly practical. It may seem surprising that reducing numerical precision has only a modest effect on model performance. Neural networks contain significant redundancy. Many learned parameters contribute only marginally to the final prediction, meaning they can tolerate small approximations without substantially affecting overall behavior. Modern quantization algorithms analyze weight distributions and selectively preserve critical information while compressing less sensitive values. This allows dramatic reductions in model size with relatively minor quality degradation. GGUF is a widely adopted file format for distributing quantized language models. Rather than storing only raw weights, GGUF packages together model weights, neural network architecture metadata, Stonecker information, vocabulary, quantization details, configuration parameters. Because all required information resides within a single file, GGUF models are easy to share, load, and deploy across multiple inference engines. Ollama is one of the most user-friendly tools for running AI models locally. It abstracts much of the complexity involved in downloading models, configuring inference engines, and exposing an API. A typical Ollama workflow involves installing Ollama, downloading a supported model, launching the model with a simple command, interacting through either the terminal or an API. Behind the scenes, Ollama manages model storage, execution, memory allocation, and request handling, making local AI accessible even to beginners. Unlike Ollama, which prioritizes ease of use, vLLM is designed for maximum inference throughput. It is widely used in production environments where multiple users simultaneously access large language models. One of its key innovations is PagedAttention, an efficient memory management technique inspired by virtual memory systems used in operating systems. PagedAttention dramatically improves utilization of the key value cache, enabling higher throughput and better GPU memory efficiency. vLLM also performs intelligent request batching, allowing multiple users to share GPU resources effectively without significantly impacting latency. Large models often exceed the VRAM available on a single graphics card. Multi-GPU inference distributes model computation across multiple GPUs, enabling much larger models to run efficiently. Several parallelization strategies exist. Tensor parallelism divides individual mathematical operations across multiple GPUs. Pipeline parallelism assigns different neural network layers to different GPUs. Data parallelism, commonly used during training, replicates entire models across GPUs to process multiple batches simultaneously. Each approach addresses different computational bottlenecks depending on the workload. Memory optimization techniques are essential for maximizing hardware utilization. Modern inference engines employ numerous strategies, including weight quantization, efficient attention mechanisms, KV cache compression, memory paging, lazy tensor loading, CPU offloading, GPU memory pooling, flash attention, and continuous batching. Together, these techniques enable models that once required enterprise hardware to run efficiently on consumer GPUs. Every conversation generates intermediate computations that the model may need later. Instead of recomputing these values for every new token, inference engines store them in the key value cache. The KV cache significantly accelerates text generation, but also consumes increasing amounts of memory as conversations grow longer. Longer context windows therefore require proportionally larger KV caches. The context window defines how much information the model can consider simultaneously. A larger context enables long conversations, entire research papers, large software repositories, books, and extensive code bases. However, increasing the context window also increases computational complexity and memory requirements. Several metrics are commonly used to evaluate local AI performance. Tokens per second measures text generation speed, time to first token measures responsiveness. Latency, time between request and response. Throughput, total requests processed over time. VRAM usage, GPU memory consumed. RAM usage, system memory consumption. GPU utilization, percentage of GPU workload. Together, these metrics provide a comprehensive picture of inference performance. For beginners seeking simplicity, Ollama provides one of the easiest entry points into local AI. Developers building production-grade AI services often prefer vLLM because of its exceptional throughput and efficient resource utilization. Users seeking broad compatibility with community-distributed models frequently choose GGUF-based ecosystems. Hardware enthusiasts interested in running increasingly capable models benefit from combining quantization, memory optimization, and multi-GPU inference. The pace of innovation in local AI continues to accelerate. Every year, models become more capable while requiring fewer computational resources. Advances in quantization, attention mechanisms, inference engines, and GPU architectures are steadily narrowing the gap between locally hosted models and their cloud-based counterparts. What once required racks of enterprise hardware can now be achieved on a well-equipped desktop workstation. As open-source models continue to improve and optimization techniques mature, local AI is becoming an increasingly viable platform for research, software development, education, business applications, and personal productivity. Running powerful AI locally is no longer a niche experiment. It represents one of the most exciting frontiers in modern computing, empowering individuals to harness cutting-edge intelligence while maintaining privacy, ownership, and control over their data. That's all for today in Dots and Arrows. See ya in the next.